In this video, we will see what type of heat pumps need to be duplicated with a second heat source for heating, also for hot water. We will see how it is used, a heat pump in hybrid mode with the second heat source. We will see how many types of heat pumps exist and why heat pump tip air to air or air to water need to be doubled with another heat source. What does it mean pump operating limit temperature? Which are the world's climate zones? Where it needs to be double the heat pump and where it will be used an electrical resistor inside the heat pump. We will see what are the percentages from the total energy needed for heating and hot water are produced by the heat pump and which are produced by the second heat source. There are many types of heat pumps. The left side represents the extraction medium and the right side represents the transfer medium. So they are air, water, air, sol air or sol water, water air or water. In reality, there are many other types, but these are the most representatives. The basic principle of heat pumps is to reverse the natural flow of heat from warmer to the colder environment by collecting an amount of heat from the colder environment and transferring it to the warmer environment. Here is the internal of a heat pump, and let's see how this natural heat flow from external average temperature goes to the collector. The heat source, the temperature of heat collector is lower as external average temperature. Here what's happening inside the heat pump, and after this one heat obtained on this element with the temperature of heat loss zones higher than the internal average temperature is transferred again through natural heat flow to internal average temperature in the building. Let's concentrate now about external zone and temperature heat collector. Through natural heat flow, we have three types of extraction media: air with temperature between -30 and +40 degrees, water with temperature between +3 to +15 degrees Celsius, and soil with temperature between 0 and +50 degrees Celsius. Now, suppose the temperature of heat collector area of the heat pump is -15 degrees, this zone. The temperature of water as a heat extraction medium is between +3 and +15 degrees Celsius, so minimum temperature difference between it and the heat collector area is +18 degrees Celsius. The temperature of soil as a heat extraction medium is between 0 and +50 degrees Celsius, so the minimum temperature difference between it and the heat collector is +15 degrees Celsius. Now let's concentrate what's happening to the air extraction media. As a heat extraction medium is between -30 and +40 degrees Celsius, so the minimum temperature difference between it and the heat collector area, it can be 0 degrees Celsius. That is, if the temperature of the air drops very low between 0 degrees Celsius, it is possible that the natural absorption of heat from the outside is greatly reduced or stopped altogether. This means that heat pumps with heat extraction medium atmospheric air, the air-to-air or air-water types, have very big problems with the steep descent of the atmospheric air temperature. In addition, with the sharp drop of the atmospheric air temperature below 0 degrees, the phenomenon of ice deposition occurs on the heat collector area, making it even more difficult taking heat from air. For the above considerations, it's clear that there is a temperature below which the heat pump can no longer operate. This is called the heat pump operating limit temperature, and it's specific for each heat pump. It would be normal for this temperature to appear on the leaflets of heat pumps, but in general, manufacturers avoid marking that there is a temperature below which the pump can no longer operate. On the other hand, most pumps have an electric resistance, power high, which compensates for the shutdown of the pump and to switch to the power plant regime. In fact, the high power electrical resistance ensures the possibility of using air or water heat pumps to temperature below minus 25 degrees as it appears in the leaflets. What the manufacturer of heat pumps forget to specify is that under TLO, the pump works as a power plant, which costs per kilowatt of thermal energy 2-3 times higher than in normal heat pump regime. The most heat pump TLO has values between minus 5 and minus 10 degrees, and that is why this problem occurs in the colder climate zones 3, 4, and 5. As seen in the graph on the left, both the pump heating power and the COP drop massively with the outside temperature. In order not to consume electricity for temperature between minus 30 and TLO, it is used for colder climate zones 3, 4, 5, a second heat source, usually a gas or pellet boiler that automatically starts below the temperature of TLO. More about using the second heat source together with heat pump, a hybrid or bivalent working mode, see the video in the description. Also in the video description, you will find for energy auditor or for passionate about energetics of buildings, two links to two different websites about energy performance of buildings and a link to a simpler video for general public about heat pumps using the second heat source. Here is the map of the world's climate zones. I've separated in 5 different zones. Zone 1 with temperature between 12 and 13 degrees Celsius. Zone 2 with temperature between 11 and 12 degrees Celsius. Zone 3 with temperature between 10 and 11 degrees Celsius. Zone 4 with temperature between 8 and 10 degrees Celsius. And Zone 5 with temperature between 6 and 8 degrees Celsius. You will take the average temperature for your city and see in what climatic zone it is. Depending on this, you will read the weight coefficients of the heat pump and the secondary source specific for that climatic zone. What percent of energy needed for heating will be provided by heat source number 2? And what percentage of energy required for hot water will be provided by heat source number 2? For warmer climate zones, the energy will be approximately 100% assured by a heat pump, but will be a small percent which when we will use the electric heater inside the heat pump. That means we don't need to invest in a gas container boiler or pellet boiler or a second heat source. For colder climate zones, the situation is different. Let's say we have a situation where the heat pump, air, water, or air ensures 85% for heating and 95% for hot water. That means that the difference, 15% for heating and 5% for hot water, will be assured by the source number 2, an example gas containing boiler, pellet boiler, etc. The calculation method of what percentage of the energy required for heating will be provided by the heat source number 2. Also, those same calculations for hot water. For hot water, the reports will be number of hours of source 2 divided 8,760 number of hours a year. The question is what percentage of the energy needed for heating will be have provided by the second heat source, taking into account that it starts below the TLO. The formula that regulates the calculation of the required heat flux of the building is this one. The formula that regulates the calculation of the outdoor start end temperature for heating, T heat, is this one. If we combine them, we obtain something like that. H or TE heat minus TE, where H is total coefficient of thermic coupling of the building, including ventilation. TE is outdoor heating start or end temperature, and TE its outdoor temperature. To calculate the heat required for heating, we will have to multiply the required heating flow by the unit of time for which the calculation is made. For example, for 1 hour is the flux or multiply 1 hour. Let's say here have a graphic for temperature for a building situated in climate zone 2, Bucharest, Romania. Here are the temperatures: normal temperature, external normal temperature, and let's suppose we have a 16 degrees, the T heat temperature where it starts or stops the heating, and this interval under this line, this area multiplied with H represent the energy necessary on the season of heating for heating. We calculate the monthly energy requirement and then add it up to calculate the annual requirement. This curve under this line. For example, in the graph above, where we have the external temperature curve for Bucharest, Romania, we have the hatched area for generally, and the formula is this, where the flux multiplied with number of hours a day and the number of days. It's a total of 744 hours in January. We continue the definition, where the definition of TE average on January is this sum. Now, if we introduce in this one, we obtain that the energy necessary for heating in January is this and this sum, and this sum we call it number of degrees hours for January. In general, for all the period, we have the ND hash for all the period. This formula can be applied throughout the whole heating period. Let's take, for example, a house in Bucharest, Romania, heated with a heat pump which has a TLO of -7 degrees. In the climatic year type for Bucharest, there is an average temperature for each of the 8,760 hours for 1 year. Let's say that the heating starts on 16 September and ends on 12 May. In this interval, we should see day by day how many temperatures are below -7 degrees and calculate this formula for each hour, where n is the number of hours with TE below -7 degrees Celsius. It would be a very time-consuming operation. Fortunately, Excel can help a lot us with this calculation. It has a function to import data from PDF Excel files to Excel. We will import data from that type climatic year for Bucharest PDF. We will get a table like the one on the left with the temperature in the natural order starting with 0 o'clock on January 1, numbered with 1 in the column marked in green to the left of the table. So this is the Excel table from importing from PDF. Maybe you have a climatic year type directly in Excel. So from 1st January, first hour to 8,760 hours, this Excel contains all of them. And I explain you, we have to look for a temperature under -7 degrees. It is a very difficult task in this variant. But we have another function in Excel we can help with it. We will continue to use Excel and copy the temperature from the left, these temperatures, to column R marked in yellow. And after that, we have a function in Excel to sort it in ascending manner from the smallest temperature to the highest. Now we can count the temperatures, the number of, of hours with temperatures in different temperature ranges, subtracting the number of rows, how many temperatures are found in a certain temperature ranges. Let's say an example for the range between minus 70.5 and minus 12.5 degrees Celsius. We will have 36 temperatures. So 36 hours have this in this interval of temperatures. Now we will count, subtracting the number of rows, how many temperatures are found in a certain temperature range. We will calculate as you see in the left sheet. So here we have for temperatures below minus 7 degrees with this formula, and here are the temperatures for all the heating period from 16 September to 12 May. The report of the 2 and the hash actually represent the heat requirement report. So this one over this one. Here is the real way we make those calculations. This is those are calculations for climate zone 1 with temperature 12 plus 12.4 degrees Celsius for Constanța, Romania. You can make an Excel spreadsheet similar to this one where you can enter your calculation for number of hours in specific intervals or go with my calculations. In the same climatic zone, two cities have two different climatic year type, but the difference between them are not so high. Let's see exactly how works this table. Here we have the range of external temperature between, and here are the ranges. Here is the temperature in the middle of the range for only for the minus 10 and between minus 10 and minus 5 degrees. I have calculations for 1 degrees range because the calculation will be too complicated for the intervals over TLO to be so detailed. So only in the interval for TLO, which it is between minus 10 degrees and minus 5 degrees, I work from 1 degree to 1 degree range, and after that the range is different. So for 27 minus 27.5 and minus 22.5, we have a mid-range of minus 25. Here is the external temperature from which the heating starts. This equilibrium external temperature, under this temperature it works heating system. It depends on the building, on its degree of thermal insulation. It does not vary so much and does not change the proportion of energies between source 1 and source 2 of heat. So that I say you can make your own Excel spreadsheet table and you can enter this specific temperature. So let's see on this minus 12.5 and minus 10 degrees. The middle temperature, average temperature is minus 11.25. The temperature for starting the heating is 15.01. The difference minus between this and this one is 26.26. Multiply with 22 is number degrees hour for this interval, for this range of temperatures is 578. We have also for all the ranges, the total NDH is 44,399, and we'll see with 1 degree, 1 degree, 1 degree how the sum for the second source increase, and the ratio between this and this is this one. And for the heat pump, the source number 1 is 100% minus 1.430. If in the leaflet of the heat pump the value of TLO is not specified, consider TLO equal minus 7 degrees Celsius. Here are the calculations for the average temperature by middle temperature for ranges. It differs a little because this is the real average temperature for all 8,760 hours from an year. Here is the table for calculating the ratios for hot water. We have the same range temperature and the numbers, the same number of hours for those ranges. And here we have only the sum of hours. So let's say till minus 10 degrees we have 22 hours, and we'll divide at all the period for hot water, which is 365 days or 24 hours a day. That means 760 hours. So this is for climate zone 1, hot water. Heating for climate zone 2, hot water for climate zone 2, heating for climate zone 3, hot water for climate zone 3, heating for climate zone 4, hot water for climate zone 4, heating for climate zone 5, hot water for climate zone 5. Again, if in the leaflet of the heat pump the value of TLO is not specified, we'll consider TLO equal minus 7 degrees Celsius.